After studying this module, you will know about the sources of the oxides of nitrogen, sulfur and carbon in the atmosphere. You will also learn about the effects of these oxides on humans, animals, plants and materials. You will learn about the control measures for atmospheric pollution due to these oxides. By this time, you are quite familiar with the composition of the atmosphere. As you know, the oxides of nitrogen, sulfur and carbon are introduced into the atmosphere through several natural processes. We will discuss the effects of these oxides on the atmosphere and the environment in this module. Carbon dioxide is a natural constituent of the Earth's atmosphere, as we already know, making up 0.033% by volume of dry air. However, excessive amounts of atmospheric carbon dioxide upsets the natural heat balance of the atmosphere due to what is known as greenhouse effect and gives rise to global warming. Carbon monoxide is formed in the atmosphere due to oxidation of methane produced in swamps and bogs and oxidation of chlorophyll in mature leaves. Elemental nitrogen is the major constituent of the Earth's atmosphere, as we have seen already. There are several natural processes by which nitrogen oxides enter the atmosphere. This could be by lightning strike due to thunderstorms to form nitric oxides, which further reacts with oxygen to give nitrogen dioxide. Nitrous oxide is released due to the action of soil microorganisms. Sulfur dioxide enters the atmosphere during volcanic eruptions. It is also produced by the oxidation of hydrogen sulfide formed by decomposition of organic matter in the absence of air. Over millennia, a certain global balance of these gases from natural sources has been achieved in the Earth's atmosphere. However, when present in excessive amounts due to human activity, most of these gases exert detrimental effects and thus become air pollutants. Let's have a look at oxides of nitrogen in the atmosphere. Nitrogen forms a series of oxides on combining with oxygen. These are nitrous oxide N2O, nitric oxide NO, nitrogen dioxide NO2, dinitrogen trioxide N2O3, dinitrogen tetroxide N2O4 and dinitrogen pentoxide N2O5. However, only the first three, that is N2O, NO and NO2, are important from the point of view of environmental pollution. They are collectively referred to as NOx. These oxides act as primary pollutants by producing toxic effects themselves, and they also act as secondary pollutants by combining with other constituents of the atmosphere to give rise to photochemical smog, acid rain and aerosols. Let's take a look at the sources of nitrogen oxides. As mentioned above, nitrogen oxides can be obtained from both natural and anthropogenic sources, with the latter accounting for only 8% of the global total. However, local concentrations, especially in urban areas, are elevated several hundredfold many a time. The burning of fossil fuels in power plants and automobiles is known to be the anthropogenic source of nitrogen oxides. In all the cases, nitrogen and oxygen in air react to form nitrogen oxides. Due to the heat produced by combustion, with a lesser contribution from the combustion of nitrogen present in the fuel itself. Nitric oxide is first formed by combination of nitrogen and oxygen. N2 plus O2 gives 2NO. Then nitrogen dioxide is formed by reaction of nitric oxide and oxygen. 2NO plus O2 gives 2NO2. Nitrogen dioxide can also be formed when nitric oxide reacts with ozone. NO plus O3 gives NO2 plus O2. Nitrous oxide, which is produced by the action of soil bacteria on nitrate fertilizers, undergoes photolysis in the stratosphere to nitric oxide or free oxygen atoms. N2O plus H nu gives NO plus N. N2O plus H nu gives N2 plus O. The nitric oxide so formed is then oxidized and nitrogen dioxide is formed. The free oxygen atoms interact with nitrous oxide to form nitric oxide. N2O plus O gives 2NO, which is then further oxidized to yield nitrogen dioxide. Nitrogen dioxide reacts with water vapors producing nitric acid, which is washed down as acid rain, or it can also react with atmospheric ammonia to give ammonium nitrate aerosol. 3NO2 plus H2O gives 2HNO3 plus NO, or NH3 plus HNO3 gives NH4NO3. Effects of nitrogen oxides. Nitrous oxide and nitric oxide ultimately form nitrogen dioxide in the atmosphere. It is nitrogen dioxide which is responsible for the detrimental effect of nitrogen oxides. Nitrogen dioxide is a primary pollutant itself and also produces secondary polluting effects. The primary effects we can take a look at first. Effects on human health. For example, nitrogen dioxide affects the inner lining of the lungs and increases chances of lung cancer and lung infections. This can give rise to wheezing, coughing, colds, flu and bronchitis, as well as by continuous or frequent exposure to higher concentrations, cancerous tumors can also grow. Continuous or frequent exposure to higher concentration of nitrogen dioxide than the normal level in ambient air may increase frequency of acute respiratory illness in children, also in the elderly. Near roadways, exposure to nitrogen dioxide is more and therefore harmful for the elderly and children, also people already having asthma. Pulmonary edema, accumulation of fluid in the lungs, may occur in susceptible people several days after the exposure, resulting in death. The maximum allowable limit for nitrogen dioxide exposure is 8 parts per million over 8-hour period. However, even at much lower levels of exposure, nitrogen dioxide can cause increased airway resistance in adults and acute bronchitis in children. Nitrogen dioxide is also a powerful eye irritant. The effects of nitrogen dioxide on vegetation can be next looked at. High levels of NO2 can have a damaging effect on vegetation, including leaf damage and reduced growth. It can make vegetation more susceptible to disease and frost damage. Even at the low concentration of 0.3 parts per million, NO2 suppresses plant growth. At higher concentration, it causes visible leaf injury through chlorosis, which is the insufficient production of chlorophyll. Food crops exposed to NO2 display chlorosis and thus to reduced yield. Secondary effects of nitrogen dioxide. Nitrogen dioxide is involved in the secondary environmental pollution phenomena, namely acid rain. Nitrogen dioxide reacts with water vapor in the atmosphere to give nitric acid as shown here, and this is further washed down as acid rain. 3NO2 plus H2O gives 2HNO3 plus NO. Photochemical smog is another secondary effect of nitrogen dioxide. In the presence of hydrocarbons and sunlight, oxides of nitrogen form this smog, which contains a variety of chemical species such as ozone and organic compounds including peroxo compounds, aldehydes, ketones, acetyl nitrates, etc. Aerosols is the third thing that can happen in the presence of nitrogen dioxide. Some of the nitric acid obtained from the reaction of nitrogen dioxide and water combines with ammonia in the atmosphere to form ammonium nitrate aerosols. NH3 plus HNO3 gives NH4NO3. So let's have a look at control measures for NOx pollution. To remove NOx pollution due to its two major sources, that is thermal power plants and automobile exhaust, control measures have to be put in place in both cases. In power plants, there are several ways of reducing nitrogen dioxide emission. One of them is reducing combustion temperature. Combustion temperature can be reduced to control the NOx pollution. The technique dilutes calories with an excess of fuel, air, flue gas or steam. This technique keeps away from the ideal stoichiometric ratio because this ratio can give higher temperatures, generating higher concentration of NOx. There are several techniques which can be applied to reduce the combustion temperature. One is use of fuel-rich mixtures. This will limit the amount of oxygen available. Second is use of fuel-lean mixtures to limit temperature by diluting energy input. The third is injecting cooled oxygen-depleted flue gas into the combustion air to dilute energy. The fourth technique is injecting cooled flue gas with added fuel, and the fifth technique is injecting water or steam. The chemical reduction of NOx. This is another technique. This provides a reducing agent such as urea to react with nitrogen oxides and reduce them to nitrogen, carbon dioxide and water. NH2CONH2 plus NO plus NO2 gives 2N2 plus CO2 plus 2H2O. Oxidation of NOx, another technique. This can be done by making use of a catalyst or by introducing hydrogen peroxide or ozone into the air flow. The N2 and N2O5 produced is scrubbed with water to give nitric acid, which can be either collected as such or neutralized by an alkaline scrubber and then sold as calcium or ammonium nitrate. Removal of nitrogen from combustion. Nitrogen can be removed from the combustion process by introducing oxygen in place of air. This gives a very intense flame which needs to be carefully controlled. In practice, instead of using any one of the above methods or any method alone, best results are obtained by using a suitable combination of the available methods. Vehicular exhaust. This is another place where nitrogen oxide emission has to be controlled. The control methods include exhaust gas recirculation, selective catalytic reduction, and a three-way catalytic converter. We can discuss each of these methods in detail. Exhaust gas recirculation. What is this technique? The amount of emitted nitrogen oxide can be reduced by cooling some of the exhaust gas and then redirecting it back to the charged air. This reduces the combustion temperature and therefore less nitrogen oxide is produced. This process is called exhaust gas recirculation or EGR. The second technique is selective catalytic reduction. In this, the concentration of nitrogen oxide is reduced by passing the exhaust gas over a catalytic converter for selective catalytic reduction also called SCR as an acronym. While exhaust gas recirculation can reduce nitrogen oxide emissions by around 40%, SCR removes up to 90% of the nitrogen oxide from exhaust gases. EGR and SCR systems can be combined to ensure better removal. SCR uses oxides of vanadium, molybdenum or tungsten on a ceramic support as catalysts. Platinum or palladium is expensive but more durable as catalyst. Finally, a three-way catalytic converter. A three-way catalytic converter removes hydrocarbons, carbon monoxide and nitrogen oxides from auto exhaust. Hydrocarbons and carbon monoxide are oxidized while nitrogen oxides are reduced. These oxidation and reduction reactions do not occur in isolation. NO reacts with CO in exhaust system as shown. 2NO plus 2CO combination passed over a catalyst gives N2 plus 2CO2. Partial reduction to nitrous oxide would also suffice since nitrous oxide is easily decomposed in the presence of a catalyst forming nitrogen and oxygen. Nitric oxide and nitrogen dioxide then interact with hydrocarbons. NOx plus hydrocarbons again passed over a catalyst N2 plus CO2 plus H2O. A three-way catalyst consists of a mixture of platinum, palladium and rhodium deposited on a high surface area honeycomb made of ceramic and metal or alumina pellets. Oxides of sulfur in the atmosphere. SOx refer to all oxides of sulfur, the two major ones being sulfur dioxide SO2 and sulfur trioxide SO3. Sulfur dioxide is a colorless gas having a pungent, irritating odor and taste. It is water soluble, forming sulfurous acid, a weak acid H2SO3. Sulfur dioxide slowly combines with oxygen in the air to form sulfur trioxide SO3. This then rapidly reacts with water to give sulfuric acid. Sources of sulfur oxides in the atmosphere. Sulfur dioxide is produced naturally from volcanoes and hot springs. Sulfur dioxide is also obtained by oxidation in air of hydrogen sulfide released from marshes and swamps on land and from biological decay in oceans. Combustion of fossil fuels, especially coal, petroleum and petroleum products at power plants, other industries and vehicles is the largest anthropogenic source of sulfur dioxide. Other sources of SO2 emissions include smelting of sulfide ores, refining of petroleum, manufacture of sulfuric acid, paper making and burning of domestic refuse. Coal combustion is the biggest source of sulfur dioxide, contributing approximately 60% of it globally. Combustion of petroleum products comes next, contributing around 21%. Sulfide ore smelting and petroleum refining contribute around 7.4% and 6.8% respectively. While the activities mentioned directly release sulfur dioxide in the atmosphere, putrefaction of organic matter, including sewage and garbage, releases hydrogen sulfide in the atmosphere, which is further oxidized to sulfur dioxide by oxygen or ozone in air. 3H2S plus 3O2 gives 2SO2 plus 2H2O. SO2 plus O3 gives SO2 plus H2O. That should read H2S plus O3 gives SO2 plus H2O. Sulfur dioxide, whether from the oxidation of H2S or from direct emission, persists in the atmosphere for 2 to 4 days, during which period it is dispersed to distant places as well as oxidized to sulfur trioxide, both chemically and photochemically. Sulfur dioxide molecules in their excited state after absorption of UV light react with oxygen as well as ozone. SO2 plus O3 in the presence of a photon of light give SO3 plus O2, SO2 plus half O2 again in the presence of light, SO3 plus O2. Chemical oxidation of sulfur dioxide by oxygen takes place in the presence of catalysts such as powdered metal oxides or dust and soot particles as well. SO2 plus half O2 particulate matter, SO3 plus O2. The sulfur trioxide formed immediately combines with water or moisture in the atmosphere to give sulfuric acid, SO3 plus H2O giving H2SO4. Effects of sulfur oxides. Let's have a look at the primary effects of sulfur oxides. These include the first being effects on human health. Sulfur dioxide is dangerous if breathed in. It causes irritation to nose, throat and airways, giving rise to coughing, wheezing, breathing problems and a feeling of tightness in the chest. Sulfur dioxide is quick acting and the symptoms can be felt in 10 to 15 minutes after breathing it in. Asthma patients are most affected by exposure to sulfur dioxide. Sulfur dioxide gas also causes eye irritation. The effect of sulfur oxides is much worsened when they are absorbed on soot particles. Sulfur oxides absorbed on particulates when inhaled pass deep within the respiratory tract, dissolve in body fluids and enter the bloodstream, the lymphatic system and the connective tissue in the lungs. This makes the airways contract spasmodically, making breathing difficult and in turn putting a strain on the affected person's heart. Higher levels of exposure to sulfur oxides and particulates lead to bronchitis and further to lung cancer. Effects on vegetation comes next. Sulfur oxides destroy plant cells and interfere with chlorophyll synthesis. High concentrations of sulfur oxide result in the opening of leaf stomata in plants, leading to excessive water loss. The sulfurous pollution reduces the number of plants and the quality of plant yield. Sulfur oxides are more dangerous in combination with other pollutants such as nitrogen oxides, fluorides and ozone. At the ecosystem level, it eliminates sensitive species, thereby affecting species distribution. Crop yields are reduced in the presence of sulfur dioxide pollution. Third, effects on materials. Stones used in making buildings, statues, etc., especially carbonate-based stones, undergo severe erosion in the presence of sulfur dioxide, causing pitting and scarring as well as discoloration. This phenomenon is called stone leprosy. In case of metal structures, SO2 accelerates corrosion reactions that occur naturally when sufficient moisture is present on a metal surface. Steel panels have been found to corrode 50% more rapidly in the presence of even 0.1 part per million of sulfur dioxide in conjunction with particulates. Painted surfaces take longer to dry and continuous exposure to sulfur oxides causes discoloration and loss of gloss, requiring frequent repainting. Paper, fabric and leather become discolored. Paper exposed to sulfur dioxide also becomes brittle. secondary effects. For example, acid rain. The SO2 and SO3 in the atmosphere are washed down with rain in the form of sulfurous and sulfuric acid, H2SO3 and H2SO4. The pH of such rain is much below the normal pH of 5.6 associated with normal rainwater, and this kind of rain is therefore called acid rain. If the oxides of sulfur and nitrogen get converted into the corresponding acids in the atmosphere, then they come down with rain and it is called wet deposition. Alternatively, the oxides may be directly absorbed by a wet surface, which could be land, vegetation or a structure, and can be transformed into acid after absorption. This is called dry deposition. Another indirect effect results from acid rain, which leaches out nutrients from plant canopy and soil. The acid runoff changes the pH of water bodies and adds large quantities of nutrients which can disturb the equilibrium of aquatic communities. Smog is another effect. Industrial smog, or London smog as it is called, contains two primary components, sulfur dioxide and particulates. These include dust and soot from burning coal. The sulfur dioxide produced from combustion of coal or other sulfur containing fossil fuels dissolves in water droplets in the atmosphere and becomes a toxic stew of thick fog and particles. The worst incident of smog in London in 1952 claimed 4,000 lives between 5th to 9th December and caused major disruption in transport due to reduced visibility. This kind of incident related to smog formation has now fortunately become a thing of the past, partly due to pollution legislation and also due to modern developments such as the widespread use of central heating, reducing the amount of coal generated in the atmosphere. Coal dust used to be a special part of the atmospheric pollution, much more in the times when there was no central heating. Control measures for SOx pollution. High sulfur content of fuel increases the emitted sulfur oxides emission, and these can be reduced by making use of low sulfur fuel like natural gas. Low sulfur oil is another option, low sulfur coal being a third option. The additional advantage of using natural gas is that it does not emit particulate matter on burning. There are two broad categories of methods for reducing the amount of sulfur oxides released into the environment from burning of coal. These would be fuel desulfurization techniques and flue gas desulfurization technique. Fuel desulfurization is removing sulfur from the fuel itself before it is burnt. One physicochemical method could be that 70% of the sulfur in high sulfur coal, which is in mineral sulfate form, present as iron pyrite FeS2 but not chemically bonded to the coal, while the rest is organically bonded sulfur. Ground coal is subjected to hydraulic washing, resulting in the settling down of the pyrites, which is heavier. The sulfur-free coal floats to the surface from where it is collected. Organic sulfur is removed by passing hydrogen gas over the coal in the presence of mixed cobalt molybdenum oxide catalyst. The organic sulfur is converted into hydrogen sulfide, which is absorbed into diethanolamine. The sulfur can then be regenerated by oxidation. Microbial method is also possible. The organic sulfur can also be removed by a microbial method in which a specific bacterial strain cultured in a sulfur limited medium where the supply of all other nutrients is abundant, is allowed to draw out the sulfur required for its metabolism from coal. It selectively metabolizes the sulfur from coal without damaging the coal. However, the method is too slow to be commonly viable. Petroleum desulfurization is achieved during the refining process, in which heat and pressure convert the organic sulfur into hydrogen sulfide. The gas rich in hydrogen sulfide is passed through a sulfur recovery plant where the H2S is oxidized to give SO2, and water and the SO2 is catalytically reduced to give elemental sulfur. The second technique is flue gas desulfurization. This can be done by several ways. For example, wet limestone scrubbing. Slurry is made by mixing crushed lime and water, which is then sprayed into the flue gases containing sulfur. Aqueous slurry of calcium sulfite is formed after the reaction of the sorbent with SO2. Subsequently, calcium sulfite formed is oxidized to calcium sulfate by introducing compressed air into the slurry. Calcium sulfate so formed is then subjected to removal of excess water and disposed of in landfills. SO2 removal can be close to 90% with this method. The limestone could also be mixed in powdered form with powdered coal in the boiler. Limestone decomposes at high temperature to give lime, which reacts with SO2 to give calcium sulfite and sulfate. CaCO3 on heating, CaO plus CO2. CaO plus SO2 gives CaSO3. CaO plus SO2 and half oxygen gives CaSO4. Though effective in reducing sulfur emissions, the method generates large amounts of sludge for disposal. The Wellman-Lord process. This process can be divided into two stages. The first is absorption. In this stage, the hot flue gases are passed through a pre-scrubber and ash, hydrogen chloride, hydrogen fluoride and SO3 are removed out of the flue gas. The gases are then cooled down and delivered to the absorption tower. A saturated solution of sodium sulfite is sprayed onto the flue gases at the top of the tower. The sodium sulfite reacts with the sulfur dioxide and forms sodium bisulfite. The concentrated bisulfite solution is then collected and passed to an evaporation system for regeneration. The next step being regeneration. Sodium bisulfite can be broken down using steam and the resulting sodium sulfite could be recycled to the flue gases. The released SO2 is then converted to elemental sulfur, sulfuric acid or liquid sulfur dioxide. The advantage of this system is that the sorbent is regenerated during the combustion process and is continuously recycled. Fluidized bed combustion is another technique. In this process, sand is used to make the bed on which combustion of coal takes place. Air is blown up from beneath the bed at high velocities. As velocity increases, particles are forced upwards and reach a level at which they remain suspended in the airstream. The bed in this state is called fluidized as it behaves like a fluid. In order to absorb the heat generated, water containing tubes are immersed in the bed. This water is converted to steam, which is used to drive a steam turbine, thus producing electricity. The movement of this fluidized material in the combustion chamber results in a transfer of heat to the water-filled tubes, and therefore operating temperatures are lower than in a conventional system. Addition of sorbent such as lime or limestone can control the SO2 emissions because it absorbs the SO2 present. The SO2 released from the coal is absorbed by the limestone and is retained within the ash, which can be regularly removed. Effective combustion takes place without causing the ash to soften, making it easy to remove the ash containing the absorbed SO2. Oxides of carbon in the atmosphere. Carbon dioxide and carbon monoxide are the main oxides of carbon. Both of them are colorless, odorless and non-irritating. Carbon dioxide is non-toxic, non-combustible and a non-supporter of combustion, while carbon monoxide is highly toxic and burns with a blue flame. The sources of carbon oxide. Carbon dioxide is present in the atmosphere at a concentration of 0.04%, which is 400 parts per million by volume. It is used by plants, algae and cyanobacteria in the process of photosynthesis. During the day, plants overall absorb carbon dioxide because the carbon dioxide required for photosynthesis is more than that produced during respiration. At night, when photosynthesis cannot occur in the absence of sunlight, some carbon dioxide is produced by plants during respiration. During respiration, carbon dioxide is produced and exhaled by humans and animals as well as plants. Carbon dioxide is also produced during organic decay and the fermentation of sugars, combustion of wood, carbohydrates and major carbon and hydrocarbon rich fossil fuels such as coal, peat, petroleum and natural gas also contributes to atmospheric carbon dioxide. Volcanoes, hot springs and geysers are natural sources of carbon dioxide. Carbon dioxide is found in lakes, deep in the sea and mixed with oil and gas deposits. It is a major greenhouse gas. The burning of carbon-based fuels increases the concentration of carbon dioxide in the atmosphere, leading to global warming. Carbon monoxide is generated by both natural and anthropogenic sources. In nature, it is produced by the oxidation of methane, a gas released from swamps, bogs and rice paddies. Mature leaves produce copious amounts of carbon monoxide due to degradation of chlorophyll. The surface waters of all the Earth's oceans release carbon monoxide to the atmosphere. Small amounts of carbon monoxide are also produced in normal animal metabolism. Combustion processes in nature, such as forest fires and volcanoes, also produce carbon monoxide. The background concentration of carbon monoxide is increasing every year due to human activity. When carbon-containing substances are partially burnt, carbon monoxide is formed. 2C plus O2 and fast burning leads to 2CO. Carbon monoxide is produced when there is not enough oxygen to form carbon dioxide, such as when operating a stove or an internal combustion engine in an enclosed space. The reaction of CO to give CO2 is slow owing to high activation energy. Hence, it occurs only when the temperature is high or when there is excess of oxygen. When there is heavy traffic, a high concentration of CO is released in the atmosphere. In cities, a high percentage of all CO emissions may be released from automobile exhaust. Industrial processes and non-transportation fuel combustion are other sources of carbon monoxide in the atmosphere. Fuel burning appliances are sources of indoor pollution by carbon monoxide and contribute to serious health risks to building occupants. Cigarette smoke contains a high concentration of carbon monoxide, up to 2%, due to incomplete combustion of tobacco. Some of the inhaled gas 0.04%, passes into the lungs of the smoker. Thus, exhaled breath of smokers contains higher amounts of carbon monoxide than that of non-smokers. Let us then look at the effects of carbon monoxide. Carbon monoxide present in air may cause headaches, nausea, fatigue, and impairment of judgment. It is breathed in excessively, it can prove fatal also. This happens because when inhaled, carbon monoxide combines with the hemoglobin in the blood, which has approximately 210 times more affinity for CO than for O2. Thus, instead of oxyhemoglobin, the complex formed in blood on inhalation of oxygen, Hb plus O2 giving HbO2, carboxyhemoglobin COHb is formed. The inhaled oxygen is carried to different parts of the body as oxyhemoglobin. The oxygen carrying capacity of blood is impaired in the presence of carbon monoxide because many hemoglobin molecules remain complexed to CO instead of O2. So, the blood has carrying capacity less for oxygen. In addition, in the presence of CO, it becomes difficult for oxyhemoglobin to release oxygen after reaching different parts of the body. The combined effect results in severe impairment of oxygen transporting ability of blood. High levels of carbon monoxide in the body thus lead to severe oxygen shortage for various bodily functions. The danger from CO exposure is greatest in infants, the elderly, and those suffering from chronic heart and lung illnesses. Distance vision, night vision, hearing ability, and mental performance are adversely affected by carbon monoxide poisoning, increasing the incidence of accidents. Carbon monoxide can cross the placental barrier, thus reducing oxygen availability for the fetus. This results in low birth weight of infants whose mothers are exposed to carbon monoxide during pregnancy. For example, pregnant women who are smokers. Higher blood levels of carbon monoxide lead to an increase in hematocrit, that is percent volume of red blood cells in blood, possibly because the body needs to make up for the RBC in which the hemoglobin is tied up with carbon monoxide. Smokers have been found to have elevated hematocrit. This increases the possibility of clot formation in blood vessels. Smokers thus have high cardiovascular morbidity and are at risk for fatal artery blockage at an early age. Where oxygen deficiency already exists, for example in individuals with anemia, chronic lung disease, or impaired circulatory system, the effects associated with carbon monoxide poisoning increase. This also happens in high altitude areas where the atmospheric oxygen concentration is already low. Normally, the threshold limit value for carbon monoxide is 50 ppm for 8-hour exposure, but for those living at an altitude of 50,000 to 80,000 feet, the limit is 25 parts per million. Control measures for carbon monoxide pollution can now be looked at. These include engine tuning in vehicles, catalytic converters, and good ventilation to prevent indoor air pollution. Engine tuning in vehicles. Carbon monoxide emissions from vehicles can be reduced by maintaining properly tuned engines and regularly checking for defects in the exhaust system. Vehicles must not be left with running engines in attached garages, and warming up of vehicles should also be done only with the outside garage door open. Catalytic converters. These are typical catalytic converters used to combine oxygen and carbon monoxide and form non-poisonous carbon dioxide. This is installed in most of the new models of cars and trucks. The concentration of carbon monoxide in gasoline engines in the absence of catalytic converters are in the range of 30,000 to over 100,000 parts per million. The three-way catalytic converter for taking care of NOx, hydrocarbons and carbon monoxide simultaneously has already been described. A good ventilation system for indoor carbon monoxide pollution. This can happen because of charcoal grills, stoves, heating systems, etc., and can be controlled by keeping the home or workplace well ventilated. Let us then recapitulate what we have learnt in this module. We have discussed about the natural and anthropogenic sources of the oxides of nitrogen, sulfur and carbon. The oxides of nitrogen, sulfur and carbon are introduced into the atmosphere through several natural processes. However, addition due to human activity raises their proportion in air to harmful levels. We have examined the damaging effects of high levels of NO2 on humans, animals and also on vegetation, including leaf damage and reduced plant growth. The burning of fossil fuels and automobile emissions are known to be anthropogenic sources of nitrogen oxides. Secondary pollution due to nitrogen oxides has also been discussed. Continuous exposure to high concentration of oxides of nitrogen result in acute respiratory illness in children and the elderly. Sulfur oxides are released from combustion of sulfur containing fossil fuels. We have discussed about the two broad categories of methods for reducing the amount of sulfur oxides released into the environment. These include fuel desulfurization techniques and flue gas desulfurization techniques. Combustion of wood, carbohydrates and major carbon and hydrocarbon rich fossil fuels such as coal, peat, petroleum and natural gas contributes to atmospheric carbon dioxide, which is a greenhouse gas. Incomplete combustion of carbon containing material results in the formation of carbon monoxide, a poisonous gas which when inhaled reduces the oxygen carrying capacity of blood. So now you are familiar with the oxides of sulfur, nitrogen and carbon which are present in the atmosphere, their sources and effects on human health and environment and the control measures exercised for them.